All right, welcome back. Let's dive right into this explainer. Today, we're going to see how exact math and key figures on a rig aren't just, homework for engineers. They are the literal lifeline preventing catastrophic disasters. Because let's be real, when you're dealing with millions of pounds of steel and intense downhole pressure, your intuition is absolutely not going to save you. You need unwavering absolute precision.
Here is what we're covering today. First up, making the connection. Then we'll move into hoisting and brake physics, tackle pressure and well control, cover casing and downhole plugs, and wrap it all up with mud math and hidden hazards. Let's get to it. Section 1. Making the connection. Now, safely screwing together thousands of feet of steel sounds pretty straightforward, right? But a single misunderstanding here can ruin an entire well. Your intuition might say that the threads do the sealing. Actually, scratch that, reality dictates otherwise. In rotary shouldered connections, it's the flat shoulder faces that actually seal when they slam together. The threads, they just pull them into contact. Because of this, you absolutely have to pull the exact makeup torque from API tables. Like, for example, roughly 25,000 to 30,000 foot-pounds for a 6 1/4 inch collar connection. You never guess, and you never ever do it just by feel. So what happens if you ignore those tables? Well, you invite in the silent killer of a drill string, under torque. If a connection is under torqued by feel, the shoulder doesn't seal properly. High-pressure mud jets through that tiny microscopic gap, and it will literally cut a channel through hardened steel in just a matter of hours. And this brilliantly illustrates why trusting the math matters so much. Diagnosing a pressure drop early is your only way to prevent the string from completely parting downhole. If you see a gradual, unexplained standpipe pressure drop while keeping a constant pump rate, that is your drill string screaming at you, "Hey, I've got a leak." Catch this washout early, and you just replace one piece. Ignore the gauges, that connection parts entirely, leaving your bits stranded at the bottom of the hole. Section 2. Hoisting and brake physics. Okay, let's step over to the Drawworks. We need to look at the exact physics that prevents 300,000 pounds of falling steel from just melting your equipment. The real danger here isn't lifting, it's lowering. We manage this using the capstan effect. The formula here is T2 equals T1 times e to the power of mu theta. It is arguably the most elegant piece of physics on the rig for brake bands and cat heads. What this equation is telling us is absolutely crucial. Friction adds tension continuously, which amplifies the driller's hand force exponentially around the drum. The tension doesn't just grow steadily along the wrap of the brake band, it multiplies. Thanks to this exponential growth, a driller pulling with just 100 pounds of force on one end can hold back literally thousands of pounds at the anchored end. But we still have to manage the heat. Lowering just one 90-foot stand releases an astonishing 27 million foot-pounds of energy as heat into the brakes. Think about that for a second. To safely manage that massive thermal load, you have to follow the friction block rule. They must be replaced as a complete set. Mixing old and new blocks gives you mixed thicknesses, which leads to partial contact. The heat concentrates on just a few blocks, and that causes brake fade, where the brakes silently lose their grip with absolutely zero warning at the lever. And while we're on brakes, here's a vital safety contrast to lock in. Never, ever park a load on the auxiliary brake. It's fantastic for absorbing energy while a load is moving, but its braking force is entirely proportional to speed, meaning when the speed drops to zero, its holding power drops to zero. Only the friction brake can actually park and hold the load. Section 3. Pressure and well control. Stepping into the well control zone, managing extreme pressure is entirely about strict numerical compliance. Blowout preventers are selected based on exact working pressure classes, like 5,000, 10,000, or 15,000 psi. But keep in mind, an untested BOP is really just a dangerous assumption. Those ratings mean absolutely nothing if the equipment hasn't been proven. That's exactly where API 53 compliance comes in. It dictates that the BOP test interval must never exceed 21 days. A BOP sits idle for weeks doing nothing until an emergency strikes. The only thing guaranteeing it'll work is the last time you tested it. Sticking strictly to this 21-day limit ensures this independent barrier is actually ready for a kick. And how do we test it? You must always run the low-pressure test, typically 250 to 350 psi, before every high-pressure test. Now, this might seem kind of counterintuitive, right? But high pressure physically forces the rubber seals into a tighter fit. If you only test at, say, 10,000 psi, you might completely mask a flaw in the rubber that would cause a major leak at a lower pressure. Section 4. Casing and downhole plugs.
Moving downhole, we look at the structural skeleton of the well, governed by burst, collapse, and tension design loads. A massive rule here. The casing head working pressure must match or exceed the BOP bolted to it. You never bolt a 10,000 psi BOP to a 5,000 psi casing head. The math explicitly forbids it. Your well control stack is an assembly, and it is only as strong as its weakest flange. A massive BOP is entirely useless if the casing head beneath it blows out.
Speaking of downhole isolation, bridge plugs typically have a differential pressure rating of 5,000 to 10,000 psi, but you must always check the direction of hold so the plug doesn't get pushed right off its seat. Some plugs only hold pressure from one direction. You aren't just picking a depth, you're verifying that the exact specs align with the forces at play. And for every single slip set operation, remember this golden rule: the bowl taper must match the slip taper. This precise geometric match is what translates a string's downward weight into the inward radial grip that keeps it safely suspended. If those tapers are off, uneven wear will either crush the pipe or let millions of pounds of steel slide right through the rig floor. No way you want that. Section 5. Mud math and hidden hazards. Finally, let's dive into mud math. Mud is a highly engineered fluid acting as your primary pressure barrier. When you're planning a kick response, literally 1 decimal point error in your Barrett formula can be the difference between a safe shift and a blowout. The exact calculation is 1470 times the difference in weight, divided by 35 minus the target weight. So jumping from 12.0 to 12.5 pounds per gallon takes roughly 33 sacks of Barrett per 100 barrels. Balancing bottom hole pressure depends entirely on getting this math right. But while you're mixing that mud, keep OSHA in mind. They limit respirable silica to just 50 micrograms per cubic meter over an 8-hour shift during bulk powder handling. Barite is essential, sure, but the silica dust it generates is a career-ending respiratory hazard. It has 0 same-day symptoms, making strict numerical compliance with this 50 microgram limit absolutely crucial for your long-term health. Now, for a hazard hiding in plain sight: trapped annular pressure. Because liquids barely compress, a heated trapped liquid leads to a massive pressure rise. If fluid is trapped between casing strings and the well starts producing hot fluids, that liquid expands. With nowhere to go, the pressure skyrockets dramatically, threatening to burst or collapse your casing. A sealed annulus is definitely not automatically a safe annulus. I'll leave you with this thought. In a world where forces are exponential and limits are absolute, knowing these key figures is your only true blueprint for survival. From the 27 million foot-pounds of energy on those brakes to the exact API makeup torque on a collar, success out here isn't about luck. It's about respecting the math. So ask yourself, are you trusting the numbers or are you just guessing? Thanks for joining me on this explainer, and I'll catch you on the next one.